Okay, so what we're gonna do is we're gonna do the qualitative aspect of, we're gonna redrive the van der Waals equation of state from kind of a more qualitative aspect. When we did the linked cluster expansion, that was far more rigorous. We're gonna set this up, and then I gave you this handout here. It turns out the van der Waals equation is gonna be it's gonna have embedded within a phase transition, which isn't obvious. I want to show you how that works, and the reason why I printed this out is there's going to be some diagrams in here. I'll draw, we're going to refer to here for better pictures, because basically they have to be drawn kind of well. They're a little on the slow side. Okay, so we're talking about another derivation for the van der Waals equation of state. And okay, over here. Here. A line here. And does that red show up okay? I think the red shows up fine. Do you agree? Yeah. Maybe I can I will pause this, and I will okay. So what we did last time, we said the van der Waals equation. And if you're spelling this is actually a low lowercase b, lowercase c, then a capital W. Okay. The van der Waals equation of state, EOS, is an example of mean field theory. And we said with mean field theory, we're going to take some particle in our system. We're going to say that this particle is going to experience some average of all the other particles. And mean field theory sometimes breaks apart, but you can still get a lot of knowledge. So the way we did this, we took one little particle here, out the ith particle, and we said there's going to be some particles in here that are some distance. Did I call them Rij? What did I call them last time? Rij away. So this is going to be the jth, we call this the jth region or jth particle. But there's a lot of particle in this jth region here. Okay, so it's not really a J, but it'll work. And it has some little region here. We said the region here is this E3 Rij, like this. That's the little region here. And we said that the interaction energy between these two, if this is Vij, this is going to be, we're going to take the interaction energy for the ith and jth particle. There's some particles in that same region here, so we're going to put this in here like that. So we said this is the interaction of this particle with all these particles here, and we said there's a certain density here. So we took this and we multiplied by the number density. This right here, this is the number of particles in the small cube D3Rij. Did I call it D3Rij or just D3R last time? D3R. D3R, okay. So get rid of the side J, sorry about that. Try to keep the same notation. So we take the number of particle densities times the volume here, so this is the number of particles. They're all more or less at the same Rij, so we take that times this. That would be the interaction energy between this and the here. And where mean field theory is going to come in, we're going to assume that this density is the same all throughout this whole region. Does that make sense? So if I want the total interaction energy, I have to take this integral here. I have to integrate it over all the region. So if I integrate this over all space, this is a triple integral, but I'm just bringing one integral because I'm lazy. I'm going to have this. And we said by definition, this is going to be minus 2a. This is a constant. So a is a constant. Why did we put that 2 there? Because I cannot, if this is a constant, I can always put a 2 in front of there. But I'm going to put the 2 in there because we're going to get another half, and I want to get rid of that half. Okay, so it's just for convenience. Why is there a minus sign here? True, but also we're gonna say this is a interaction energy, so it's gonna overall lower the energy, so that's why we put the minus sign here. We can treat this as positive. Okay, so that's what this is gonna be for this particle and all the other regions around here. But now what do we have to do? We just don't have the science particle, we have, you know, this one and this one, this one and this one, and we have all these other particles we have to sum over. So what we have to do is we take that value there, we multiply by all the other particles. So, oh, there's an n here too, I'm sorry, I took out the n here. So there's also a factor of n here like that, so I took this n out of here like that.
You moved it, or it's on both?
Well, it's on, okay, so in other words, if I were to do, let me be precise here. So if I were to have this whole guy here. And pull this n out. And this whole region here is what I'm calling minus 2a. So this gives us the minus 2a. That makes sense? We have this. And this is for, I'll put this over here. So this is just for the ith particle and all the other regions. Now we have to count for all the pairs. And so we have minus n minus one other pairs. We can over count, so we can have this. So this factor here, this accounts for all combination of particles. And this 1/2 here is to avoid double counting. That's what this gives us. It gives us at the total interaction energy. Is going to be this, and we're going to say that n is large. Okay, so we can say n is large. This is basically just n instead of n minus 1. It's going to be this 2a n little n. This little n, since it's the number density, it's the number of particles we're dividing in the system. That 2 goes out. Sorry about that. This is going to be this a n squared over v with a minus sign. So this is your interaction energy. I think that's more or less how far we got on Friday. Did drop more. Are there any questions in that? So that's from Friday. Okay. Now, what did we say? I said 4 an ideal gas. Remember what the Z is for an ideal gas? That word quantum concentration NQ times volume. And the particles are all non-interacting. So what happens to your partition function when you have these non-interacting systems? So this would be for one particle. And this is Z for one particle.
You raise it
To the number of particles. So then this gets raised to the n. And then so we had this guy here. And this NQ be raised to the n. Okay. Now, we also said if we divide this through by n factorial if we have identical particles. Well, I don't need that factor right now, so I'm not going to put that in there. But there is this would be divided by n factorial. I'm going to put that in later on when we talk about something, but not right now. Okay.
Oh, I do not remember that.
Okay, now call this ZID.
That's not bad.
And this is ideal. Okay. Okay. Okay, now there's another assumption we made for the ideal gas. For the ideal gas, what do we assume is the volume of any ideal gas particle?
Nothing.
Nothing. So the volume of an ideal gas particle is 0. So one thing I can do, if I have a non-ideal gas, okay, I can assume that the particles have a volume. Well, let's assume that our real molecules or atoms, doesn't matter which we're dealing with, have a volume. So what would be one of the dumb corrections we can do here? So V is the volume of our room. But now it's not the total volume of the room. We have to subtract off the volume of our ideal that's being taken up by the gas molecules. So if B is the volume for one of them, if we have N molecules, what we should we then subtract from this volume? And B. So one correction we can have is I can say that this is the ideal. Now I'm going to go to NQ V minus NV all raised to the N. Okay, makes sense. So now we've come up for the volume here. Now we want to come for this. So recall, what is your Helmholtz free energy given by? Minus
minus KBT.
minus KBT
Of that.
ln of Z. Okay, and also F is, what is it in terms of the what are you talking about transformation?
U minus TS.
U minus TS. Okay, so what I can do is I can do the following argument. I can say that this F for the van der Waals equation. So I'm going to say F for the van der Waals. I'm just going to abbreviate that, PDW. Okay, it's going to equal what? This is going to equal F for the ideal gas. Okay, now the fact that this is coming in U here, normally with the U for the ideal gas, we'd only have the kinetic energy, which is going the ideal part. But now we have this interaction energy. Since it just comes in here, I'm just going to tack this along here. So plus I'm going to say plus the interaction energy between particles. Does that make sense? So what I'm going to have is I'm going to say V van der Waals equals minus KBT, the ln of Z ideal. Meaning where the Z ideal is not going to be this form here. Okay. And then I'm going to add to this my buddy over here, minus A n squared over V. Okay. Let's beat on this a little bit more. So this gives me minus n kBt. This n comes down, and the ln of nq, d minus nb here. Okay, minus a n squared over v. Okay, let me stop here. Does that part make sense? Now, how do we get a pressure out of this? How is pressure related to F?
Yeah, or F or A.
P is minus partial of F back to V. Hey, let's say you didn't remember that. You tell me how you get that. Thus that. Okay. Thus that. I'm not seeing A and I'm not seeing F in here.
That's A.
A is F. Okay. G, F, T, what's missing then? P. What depends on T and P? G. This means this has to be H. Which way is positive? Okay. You tell me how to get this here. from the bus fat. The partial of A, which is F, with respect to V, is minus P. Okay, bus fat. Here, I'll start off by writing the minus sign. Like I gave it away. Okay, now you do the rest of it for me. So I get minus ABTN
minus n.
Okay, so this is NQ B minus NB.
Oh, I say minus n. It's just one then. Oh, the n.
Okay, there's that part. Now let's do this guy. Minus AN squared plus the derivative of B 1 over B
Minus 1 over b squared.
minus B of minus 2 power. And this stands for a little bracket here. P equals, okay, these cancel here, this makes it positive. This is N K Tn over B minus NB. Okay, minus A N squared over B. Does that make sense?
I really just popped out. It's cool.
Bus fat. That's all this will be in the point where you have to chant bus fat. And you do that one. That's it. Do face bending like this, you know. That's what you do. Okay, so this gives us P plus A N squared over V squared. Take over my buddy here. P minus N over P equals N KBT. Okay, so this is our van der Waals equation state. You want your equation of states do for us again?
P, V in the same.
Yeah, the PT and V, it's going to show you how they're all connected. And you can get equation of states for everything. My advisor, one thing he did, he had an equation of state for neutron stars. And so that made him, it's called the Pondhara-Friedman equation of state. Can do a lot of that. Okay. That makes sense. And then we can plot these for constant t. So for constant t, okay, what's called a constant t? Constant t is referred to a isotherm. So these are for isotherms. You can plot this p versus t. I mean p versus v. You kind of get things like that. Now, I can keep on lowering the t and what happens. So this is for some t1 here. And I can lower the t again, and I'll get some t2 here. But something really odd is going to happen if I keep on lowering this. What happens is you start getting the following. You're going to get this line coming down here. You're going to get this weird behavior like this. It's going to go like this. This. Okay, you're going to get this weird behavior like that. That makes sense? Now, if you actually increase the temperature, what happens is you get this. Eventually you get that. Okay. So let's figure out a couple things here. Tell me about these 2 points here. What's happening at those 2 points? Yeah, both of these points. Partial P with respect to V is 0. Now, what's happening to these 2 points the further up we get? This point and this point, this point, this point, this point, this point. What's happening to those 2 points? They're coming together. So at this point right here, what happens? So if I call this 1, or if I call this 2, this point here, basically the 2 points. 2 points for here. merge. Never. Further, there's another name for this here. What would a mathematician call that? Something else going on there.
Oh, which part?
Right here. What do you think happens to this part here? Look at the second derivative. That's also going to be,
What's the name? There's the C.
that's also going to be 0. Okay, this right here is called a critical point. So this right here, at this point here, this is called the critical point. This is the point where this equals 0 and the second derivative equals 0 is called the critical point. Okay. We're gonna get back to that. Right?
So what's the difference, like first, second derivative ending?
Well, the second derivative is the derivative of the derivative of this. So if you look at the rate of change of this at that point, it's not changing. So you have a slope. So here you can see that the slope is going to change here. Slope is going to change here, change here, change here. At this point here, if you have that
Oh,
slope,
okay.
that slope is not changing along that point there. Yeah. Is an inflection point. That makes sense? Now, question is, what does this represent here? So what does the behavior represent? If anything. Okay, naively, what would we say? Naively, we would say we have a model for an ideal gas, and you just say, well, the model is breaking down. So naively, one might expect that our simple model for a gas is breaking down. Okay. However, maybe it's representing something else. However, possibly it's modeling another behavior. So what happens if I have a gas and I start cooling it more and more and more? What can happen to a gas then? It can turn into a liquid. So maybe what this is showing is actually the transition between a liquid and a gas. So if you actually look at the liquid gas transition, so possibly this odd behavior is somehow capturing the phase, the liquid gas phase transition. What happens in that case? You have your pressure here and your volume here. I'll talk about what it would really look like. So if I had a liquid over here, here's a liquid. This is that constant T. So here's a liquid. I'm going to reach some point here. It's gonna start going through a transition. And when it goes through a transition, you get this behavior here like this. That goes flat. At this point here, it's all gas, it's all liquid. At this point here, it's all gas. And then it goes like this. What's going to happen in this flat region here as we go along here? If I ask the composition along here, what's going to happen? Yeah, here it's all liquid, here it's all gas. As you go along here, basically you have a liquid gas composite. As you go along here, you get less and less liquid and more gas. Okay. But what happens here is that when you actually look at this behavior here, this behavior is like that. So this behavior here possibly is modeling that. Now the question is, how do you connect this to that? Okay, does this make sense? Let me put this all together and then you can see a little bit more. So if I take that diagram I had initially and put this together. Initially, we had this pressure here versus volume. And we said that we could come down here like this, and this. And okay, so we said if we looked at these little points here like this. This represents is something like this. So when you actually do the experiment, what you find you get something like this. Okay, here's our critical point. You actually do the experiment, you actually do something like this. It looks better than that, but that's what you get here. So you get this little dotted region here, and this little dotted region here. This is the liquid. This is coexistence. Okay, of liquid and gas. Get this graph right here, and this right here is your critical point. If you go above that point, what happens?
You just.
You're here. You're all gas. This is all gas. Okay. So the question is, how can you you have this little, I drew a little straight line here. The equation itself has this little wiggle in it. How can you get these connected here? Okay, what we're going to do, let's look at actually the Gibbs free energy, and this is from that book Schrader. I handed this out to you. So for those of you on the films, I mean watching this on video, pause this and pull this out. So if you pull this out on page 182, he actually goes through a derivation for how you get G. Now, just so you know, this is going to become a daily homework. I want you to fill in the steps here. I'll write this up nice and neat. But what you're going to do, you're going to fill in the steps going from here to here. It's not that hard, but you're going to fill in the steps. So, in a future daily homework, you will fill in steps on page 182 of the handout. Okay, so what he does here, he does the following. He says here's DG. He's going to take constant T and he's going to end up with this equation here. Okay. How'd you get this quantity here? You're going to get it from this.
Oh,
You get it from that. If you do this, you end up with this. And then if you integrate that, he tells you how to integrate it, but you're going to actually go through the steps again. Go through the steps, you're going to get G equals minus N KBT ln of V minus NB plus N KBT times NB over N minus V minus NB minus 2A N squared over V. And plus some integration comes. Everything in the class. Okay, so that'll be a daily homework, and that's basically all you're going to do is put in the steps. It's not that hard, but it's just I don't want to class out how to make a good daily homework. Okay, that makes sense. Now here's the funky part. Let's take this graph here. And it gives these points names. Okay. So he calls this point 6, point 5, 4, 3, 2, 1. I said 3 for a second. Okay. And what he's going to do, he's going to plot G versus P. He really plots it over this one critical point, but it doesn't really matter here like this. Okay. And he gets an absolutely bizarre shape. So if you look at this 183 here, it's this figure where it says 5.21. What happens here is, and he's going to go this way with it like this. He's going to go this way. So we start off at 1. So this kind of goes up like this. This is point 1. Come up here to point 2. This is point 2. Then he goes up here to point 3. This is point 3. Just tell me in terms of words, how would you go about doing this? Because I actually might make you do this on Excel, but I have to do it myself to make sure that's possible. Tell me how you do this. You gotta do it yourself. The problem here is that this G only depends on V. Okay, this is for constant T. So how are you making a G versus P graph? As for a ideal gas, we can't do that.
Van der Waals equation.
The Van der Waals equation. So what do we have? We don't P is. Okay, so we can write P in terms of V, so your T is fixed. You guess the value of V. Get your value of V in here, you get your value of V. And then for that same value of V, you put it into the van der Waals equation of state and you get P. And then you plot it, and you keep on doing this.
Oh, so we find V and then.
You guess V,
Oh.
so you're gonna guess some value of V. Okay, you put that in here to get G. And then you put that same value of V in your van der Waals equation of state, and that gives you P. Then you plot that corresponding value of P in the G. Okay, now so far you could say, well, this looks fine, nothing wrong here. But here's where it gets funky. And you put in the next point. This comes over here like this. And this is 4.
Oh, no.
Okay, then you put in 0.5, and it comes over here. And this is 0.5. And then this comes back here. Let's do this down a little bit more. And that's your 0.5 here. Then you go back here. Now this becomes 0.6. Actually, this goes lower. Then that goes on like this. This becomes this 0.7. Okay, when you're getting something like this, what does that probably mean is happening here? Okay, what do systems strive for? At equilibrium, systems strive for a minimum value of G. Okay, so you're trying for this value, minimum value of G. The fact that you're getting this bizarre loop, what does it mean? It probably means that your problem is unphysical. Your model is unphysical. So this is occurring basically when we're getting this weird loop part here. And we suspected this was unphysical due to the model that we're using. And you're getting this unphysical behavior here as well. Now here's the interesting part. So this is just this. This is an indication. Our model is unphysical. But it corresponds to this real behavior like that. And real is actually, if you translate that, that means unphysical. Good to know. But now what happens here is if you go around this whole loop here, if you go boom, boom, boom around this whole loop, what's the change in G? At point 2, you're here. You go around the loop. As you get back here to G, what are you back at? The same value of G. So the integral of that dg around that loop gives you what? Gives you 0. Okay. Now Maxwell did something. I'm going to say what he did, and then I'll show you how we went about doing it. This just shows you just how smart Maxwell is. The question is, well, how on earth can you draw this line here? Well, Maxwell realized is that if you look at the area here, if I look at this area here, I look at this area here, these two areas cancel each other. And that's how you determine that line. You have a line here in such a way that these two contributions cancel each other. That's how you get that straight line. This is called Maxwell's construction. So the equal areas, the areas cancel. This is called Maxwell's equal area construction. Okay, now what I want to do is you could say, well, how on earth do you even know if they cancel? I'm going to give you his construction. So what he's going to do is going to make use of this, and he's going to plot this in a very interesting fashion. So what you're going to show in that same daily homework. If you turn the page here, okay, I guess we could just do it here. So, oh, there's really nothing else to do. Oh, damn it. No, you can say it mean that. So this is what Maxwell did. So we know that around this loop here, with this EG. Okay. So what he does here, he says a constant T, what do we know here? I can say that this is partial G with respect to pressure here. Okay. Constant T dP. And this right here, this is nothing but our V. And then he does something here, which is not one bit obvious. He's gonna plot V versus P. Okay. Now, you have to rotate this in your head. If you have P versus V here, you know that this looks like that. So now if you rotate this in your head, what do you get? You get this shape here like this. So if you have your point here like this, so this is 0.6, this is 0.2 here like that. If you do that one, you're going to get this vertical line like this. This is your 0.6, 5, 4, 3, 2. There's a reason I printed this out.
Yeah.
That line should be bent a little bit more. Okay, so let's go through and go around the whole loop. So to go around the whole loop, what do? We're going to start at 0.2, okay, then we're going to 0.3. So if I go from 2 to 3 here, 2 to 3 along the loop here, what is that going to give me? If I go from 2 to 3. That's going to give me this area here. That makes sense? Now, so it goes from here to here. Now, if I go from 3 to 4, so I'm going back this way. If I go from 3 to 4, what does that give me? Well, it gives me this area here, but I'm going the other way, so this is negative area. This part here is a positive area. This part here is a negative area. If you add those two parts together, what are you left with? You're left with basically this area here. That's positive. Okay. Now what happens? Now I'm going from 4 to 5. So I'm going from 4 to 5 this way. So that's going to give me this right here. Now is that positive or negative? I'm going this way.
Oh, okay.
Okay. So I'm going from 4 to 5. So this gives me negative area. And then what I'm doing now, I'm going from 5 to 6. And that's going to give me this area. That's going to be positive. I should, that's negative. This is positive. So what's going to happen? These two are going to cancel, and that's going to be now this area. This area here, this is negative area. What you're left with is that here's your positive area, and here's your negative area. When you add those two together, you have to get 0. So that's why this area here cancels that area here. That's how you determine how you draw the straight line. Now the question is this accurate? Okay, as far as if you compare this to a real liquid, you get the correct qualitative behavior, but the numbers aren't quite right. So this gives you the qualitative behavior of the liquid gas transition, but the numbers don't work. And the fact that this stupid model, which has no business of even working in this regime, the fact that it even can model any of that liquid gas transitions, I think is stunning. Okay, people look broken.
There's a lot of lines.
What do we, just
I
what do
get
we
it, I
exclude
get
there?
it.
Okay, the question, okay, so we have the sun physical behavior here,
Yes.
okay? And that corresponds to that unfigured physical behavior here. And we know that in a gas transition, well, the liquid gas transition, but their actual behavior is that. Okay, so we said, well, maybe what we have in this case here, that maybe what we have here is that this comes down here like this, is flat like that, and then down here like that.
I needed those areas to cancel.
And so what we did here is we said, well, how can you even get that? Well, we plotted in the Gibbs energy versus pressure. We get this bizarre loop here, and this bizarre loop here is corresponding to the sun physical behavior here. We said, okay, so this is all in physical here, but what do we know about this weird loop? This weird loop, when we come around here, we start at 2, Go all the way around here, we come back at 6, the G's are the same at 2 and 6. So the total DG for this, around the whole loop, it has to be 0. Okay? And so we could say, well, what on earth does that mean? Okay? Go through the argument here, but this can be rewritten as VDP. So then we did something bizarre here. We plotted the volume versus the pressure. They gave us this rate graph here. If you go through step by step, let me try putting it step by step.
I think I got that part.
Okay. Okay, that's fine. This area here has to cancel that area there, and that tells you where to draw this straight line. That's called Maxwell's equal area. So the question is, you have this graph here.
So that's how.
Right.
The model works.
Correct.
Okay.
And
That's
the
how the
question
model
is-
shows the
Yeah.
transition.
Correct. And the question is, we want to draw a straight line here, because we know that's what's physical. The question is, where do you draw that straight line? Is it here? Is it here? No, is it here?
Wherever the.
Okay, what Maxwell showed is that actually these two areas have to be the same. That's where you draw that straight line. It's called Maxwell's equal area calculation.
So they're able to turn that loopy thing into something helpful.
Yep, exactly. Okay, and again, qualitatively it's correct. Quantitatively it doesn't work at all. But qualitatively, does that make sense? Okay, but that's from, and again, this model, we weren't even trying to get that. That just came out of left field. This should just, if I were Maxwell saw that, I would just say, doesn't work mathematically, and it's just a simple model. We shouldn't be surprised that the model falls apart, and I would just neglect the model. You're smarter. Hold on. That makes sense? He actually died. I think he died actually relatively young. I think he had cancer. Okay.
What?
So
I thought he does
he died. Not all. There's one.
One.
No. Okay. Well, executive method. There's Cartan. He's a French mathematician, some physicist. He didn't start doing a lot of his really high-end work, I think, until his like his 50s or 60s. And he lived for like forever. He got up way into his 90s. I did really high-end work all the way through that whole life. Hans Bethe is another one too. He did develop some sort of dementia, but not until later on in life. But he did significant work all the way through all his life. He lived up, I think, into his like late 80s, maybe 90s. Iraq, I think, made it up into his 90s as well. Drobly, same thing. So they don't know about it. Okay, which is good. The most interesting one is oh good grief, Galois is a mathematician. Okay, so this might be apocryphal, but it's such a good story, it has to be told. Okay, so what is he famous for? Okay, if you have, a quadratic equation, but you can write a solution x equals 12, it's quadratic equation. Suppose instead you have like ax to the 5th plus bx to the 4th, all the way down to, whatever your, you have a quintic. Can you write an equation similar for that where x equals?
I can't.
A general one that works for any quintic. You can't. It's actually impossible.
Oh, is he the one?
It's called the insolubility of the quintic. Meaning you can solve it, but you can't write an explicit expression like you can in the quadratic. He's the one who solved it. Now here's the part where, and that no one questions that. Here's the part which might be apocryphal. Okay, he did it one day, one night, and then after he did his derivation, the claim is that he had a duel. He went into the duel, which evidently you don't want to go into a duel. He didn't come out of the duel, and that was it for him. So his only major contribution was basically the work he did, just before he had a duel.
I think I heard that story somewhere.
Whether it's true or not, I don't know, but it's a good story.
That's
Okay.
okay.
So don't get into it. Okay. Have a good day.
Who's like the best physicist or whatever?
I would say giraffe.
I was gonna say direct.
You always talk pretty high.
Direct is singing. Direct is a smart dude.